Hi, this is Jeff Heaton. Welcome to Applications of Deep Learning with Washington University. This is Module 4, Training a Neural Network, Part 3, Cross-Validation. We looked at this a little bit already, but now we're going to see more about cross-validation and how to actually set it up and actually train a neural network in this mode. So just to review, what cross-validation is a method where we take our data set and we are going to divide it into 5 folds, or 10 folds, or however many folds you're going to have. You could have 100 folds if you so desire. It's going to take a while to train if you choose 100 folds, but the most common numbers are 5 or 10. You take each of these folds and you create 5, or however many folds you have, individual training sets, training and validation splits. So you have fold 1 will be the validation set first, fold 2 will be the validation set second, fold 3, third, fourth, on the fourth fold, or the fourth train and validation set that you have, and 5 for the validation, or for the final fold. So basically each fold gets a chance to be the validation set once. The remaining folds are concatenated together and become the training set. You are then going to train 5 neural networks, and you will now have 5 out-of-sample predictions because you predicted on the training set, or on the validation set, and trained on the training set. You now have out-of-sample predictions for the entire data set. This is great because you don't have to waste any of your training data. You can truly get a prediction on the entire thing and evaluate the accuracy or root mean square on the entire thing. Now this does give you 5 neural networks, so what you need to do with those is typically you'll figure out the average number of epochs that it took to train all of these, and you will collapse all of the data back together and train on the entire set for that number of iterations. Because now you know the optimal number of iterations or epochs to train for, so you can train on the entire set. You don't need to keep a validation fold out at that point. Or you can keep all 5 neural networks, use them all to predict, and average the predictions from them. So let's look at how we would set up regression with cross-validation. So the following code trains the miles per gallon using a 5-fold cross-validation. This is pretty similar to what we've had before, but we are going to shuffle. That way, when we do those the folds, we don't have to worry about there being any order in the original training set that we had, or the original data set. We're going to get the names of the cars off just like before because we're going to remove those, and then we remove them, we drop them. We fill in the missing median for horsepower because some of the values are missing for horsepower. We just fill in the median value there. Then we split it into the x and the y. Y is going to be miles per gallon. X is the other things that you're trying to predict. And this is where it gets just a little different. You will have k-fold 5. You're having 5 folds. And now we need to keep track of our out-of-sample y. Those are going to be our predictions. We're going to build them up just like we had up here, fold by fold by fold. So we're going to loop through 5 times, training 5 neural networks, and each time through we're going to build the subsequent fold until we have out-of-sample predictions for everything. This is the out-of-sample y, so these are the correct values that we're comparing it against, and these are our predictions. So these are y hat, or our predictions. Then we're going to loop over the entire set, all 5 training folds. We're going to keep track of what fold we're on so that we can print it. This is how you break apart your X train, Y train, X test, Y test. Because you need X and Y, you're going to fit on the trains, and you're going to validate on the X and Y test. Then we create our neural network, and I'm going to use 5 for the hidden layer. I like that. I'm sorry, that is actually the output. So we're going to use, we could put a 5 in there. In fact, I'm going to modify that so it's somewhat consistent with the previous one. This is how you add hidden layers. So now we have a hidden layer. You don't want to copy that input there because it's not the input layer. We're going to create our early stop just like we did before, and we're going to fit it to 10,000 or 1,000 epochs. It probably won't go that far because the early stop will stop it. So we're early stopping on that validation fold for each one, each of the 5 folds. Then at the end, once it's fit, we're going to predict on it. We're going to take the out of sample Y, which holds the correct answers, and we're going to append the Y test to that, and we're going to also look at our out of sample predictions and add to it the predictions that we just made. So these two ensure that at the end, out of sample Y has all of the Y values that you want to compare it against, the correct answers. Out of sample prediction has what your neural network actually predicted. And then we're going to calculate a root mean square error and print out each fold's root mean square error. At the end of this whole thing, we're going to take the out of sample Y and concatenate it all together because we have the 5 folds. We need to crunch that together. Same thing for the predictions. So that combines your folds into one. They're all still in the same order. They're just combined. And then we're going to calculate the score on the entire thing, on all of the out of samples, the Y's versus the prediction. Out of sample Y is the right answer. Out of sample prediction is what the neural network predicted. We're going to calculate the whole thing. And we are going to then print out the final root mean square. I'm going to show you also how to write out a file that contains your predictions. When we get to the Kaggle assignment, you'll need to do this. You'll need to write out your submit file so that you can send it to Kaggle. And you will essentially, anytime you would want your output from your neural network, maybe you want to share it with colleagues in Excel or something like that, it's handy to be able to write that to a CSV file. So I am going to create an out of sample data frame, and I am going to concatenate the original data frame and then the out of sample Y and the out of sample prediction. So you're going to have your first columns is just the data that you already had, and then we're going to have the Y, the correct answer, and then the prediction right next to that. And we're just going to write it. If we run this part, you'll see it's doing fold 1. It early stopped at 255, and root mean square error was 8.5. Second fold did a little better. Fourth fold, fifth fold, and at the end, your not too good a one, I've seen better, but 8.56 is essentially the average of all of those, or taking all of those out of sample predictions and essentially combining them together. So that is how you did cross-validation with classification. Now, or regression, I'm sorry. Now we're going to do it with classification. This program here is a great starting point for many of the assignments throughout the semester when I have you do a regression on a neural network. Classification with cross-validation is extremely similar to that. We'll use the iris just to keep it consistent with some of our previous examples, and then we'll do more complicated data sets later. We start by loading in from the data directory, the iris. We're going to shuffle it just like we did for regression. And we're going to separate it into an X and a Y, where Y is going to be the species and X are those 4 inputs that you pass into the iris data set, or that you pass in from the iris data set into the neural network. You create 5 folds. And we are going to have our out-of-sample Y and our out-of-sample prediction just like before. We're going to loop through all of those 5 folds, print out what fold we're on, and we are going to extract the training and test. X and Y train are what we're going to train it on. X and Y test are what we're going to evaluate it on. We create our neural network. We have 50 in the first hidden layer, 25 in the second. And then we're going to output, so it's softmax and categorical cross entropy because this is classification. We're going to early stop on the validation loss, patience of up to 25, and then we fit, using the monitor and up to 1,000 epochs. You could make that 1,000,000, it wouldn't matter. The early stop is going to stop you. Then we call the model predict. We append together the out-of-sample just like before. We get the prediction, but this time we're going to take the argmax, just like we did before. So it changes all those 3 probabilities for the 3 irises into one classification of 0, 1, or 2, depending on which had the highest probability, because we're going to calculate accuracy. So then this is an important step here that we have to do for classification that we do not do with regression. We are taking the Y test, which has been the 2xy, converted that into dummy variables, so you're going to have 3 columns in this. This just collapses that back to 0, 1, 2, whatever for the 3 irises. That way you can compare the 2. This collapsing is just like we did in the previous module when we showed how to do this for classification and evaluate the accuracy. Actually, in the previous part of this module is where we first learned to do this part. So then we print out the fold score in accuracy, and we continue. We do this for all 5. This part is really pretty similar to what we did for regression. We are going to concatenate together the out-of-sample Ys, concatenate together the predictions on the second one, and we're going to create a comparison just like we did up here. So we had a Y compare up here. We're going to create a out-of-sample Y compare across all of them now so that we have something to compare against without having dummy variables. And we now calculate the accuracy and we print the final accuracy. And we do just like before. We write the output and the expected and the actual to a output CSV, which is file name write, which was defined up here. So this is your iris out of sample prediction, just like we did the miles per gallon out of sample prediction earlier. All right, that is cross-validation for both classification and regression. I did mention earlier you could keep a holdout set, and the holdout set is separate even from these. It's a third set that you might use at the very, very end just to validate everything. The holdout set, this is what it would look like essentially. You're going to keep a holdout and then the 5 folds. This gets held to the very, very end. So you'll do everything just like you did on the final validation, or on the cross-validation, train with all of these, get the out of sample. But then at the very, very end, you validate it with the holdout. So let's see how we do that. This is very similar to everything we've done. We're loading the auto miles per gallon. We're encoding it so that it's ready for that. We then shuffle it just like before. We split it into X and Y just like before, except here we're taking the 10% holdout. So we now have a main and a holdout. The main is what we're going to split into the 5 folds. The holdout we're setting aside so that we can use it later. We create our 5 folds, and we loop through very similar to before. There is really no difference between this and the miles per gallon one that we just looked at. So I won't really go through that. I will put in a second hidden layer just to make it consistent with what I had changed earlier. Not necessarily a big network, but it will form a prediction. And then at the end, this is where it gets a little bit different. We're going to build the out-of-sample just like before, and we're going to print the cross-validated out-of-sample score. It's the same as before. This is different, though. We are, now first of all, like I told you before, we are training 5 neural networks, one for each. We're just choosing the last neural network. You could retrain, basically you need some neural network at the end. Here we're just picking the last one. So whatever was the last one that got put into model, that's the one we're going to use. And we predict based on the holdout. And now we calculate the error based on this. So looking at this, we train on all of these. We generate an out-of-sample score for all of those. And then we finally evaluate them on the holdout. This gives us increased confidence that we picked the right number of epochs to train, and that whatever that final holdout score is most likely what our neural network will give on new data coming in. Similar to before, where one particular fold is not as good as the others, probably an outlier falling into that fold. And it goes through all of these. And that's the cross-validated score. Holdout score is usually higher, and that gives you sort of a better idea. So neural network could definitely do with some tuning to get better scores there. Although it's a small data set already, by using the holdout, we are sacrificing some accuracy. We really won't do holdout sets in this class other than Kaggle. For that reason, we sort of limit our data. We'll just use 5-fold cross-validation most commonly. Okay, I'll show you one last thing. This is a common area of confusion for students because of a change that was made in scikit-learn. So if you look at where I'm pulling in the cross-validated results, which is right here, I'm pulling in the utility function. Notice it comes from model selection. That's the latest version of scikit-learn. You want to use the one that has model selection. This one down here is the newest and most correct. This one is the older, works for now, may not work in the future, but it generates a big warning. And there you can see it's warning you that they might get rid of this in the future. They probably will. Students will sometimes run into this because they will look at Stack Overflow and they'll find example code that was written when this was the correct way to do it. If you get that warning, that's why. Convert it to this code down here so that you're using, notice there's no warning, and it does the same thing. It's getting it from model selection. Don't use the one that's scikit-learn cross-validation. It's an annoying breaking change that scikit-learn introduced, but you need to update to the latest code. Now, just talking about, we'll see more about Kaggle later, but Kaggle is a site, so you can see, this is my Kaggle page. I've competed in a couple of competitions since I updated that page. That page says I had competed in one, but I've competed in in 3 competitions currently. The first 2 I did pretty good in, top 10%, top 7%. So those 2 alone were 2 bronze medals. That was enough to become a Kaggle competitions expert. Ideally, I'd like to become a master, but I haven't quite gotten to that yet. I'll talk more about this one later, but this was a this was a particularly strange competition that I started in and then realized the data were very, very difficult to predict. So I ended up exiting and ended up with just a 40%. I'll show you what is the situation with that one. So I did pretty good in 2 and absolutely lousy in a 3rd. So that is my experience with Kaggle so far. But Kaggle gives you competitions where if you look at these, there's the Zillow challenge. You could literally win $1.2 million or $1.5 million if you could win one of these top 2. So that is Kaggle. It has a lot to do with the cross-validation. So let me show you how they compare it. Kaggle, you get data sets from businesses, and they want the best data scientists in the world to compete on it and see who wins it. And whoever wins it gets money. You send the solution set to Kaggle, and that has the X's and the Y's. So those are all the answers. If you could submit these Y's, you would win. So you're trying to fit to that value. What Kaggle gives you is this. They take the entire data set, they break it into a training set and into a test set. You train on the training part because they gave you the Y's, and then you predict on the test set. But what they do is they keep a final holdout this whole thing is called the leaderboard. So you submit your answers for these. You don't have to submit your model. You submit just the answers, what you think the Y's are for here. And they score you on it, and they give you some sort of a score as the competition is going. And as the competition is going, they give you the public score. You don't know which belongs to which of these 2. You just get a score as you're competing. And at the very, very end, to keep people from overfitting to the public leaderboard and making adjustments to improve their temporary score on the public leaderboard, they keep a private leaderboard as well. And you don't know which of your answers are in which, but at the end, they evaluate you here. And if you've done a good job of preventing overfitting, and these 2 are fairly representative of each other, your score on the public leaderboard and private leaderboard should be pretty similar. We'll see more about that when we get to Kaggle, but Kaggle is very much based on the holdout set. So you really have a training, a test, the public leaderboard, and then a final holdout, which is the private leaderboard. And then the last thing is managing hyperparameters. So you can set activation. You can use different activation functions. Usually you use the rectified linear unit. But you can use sigmoid or tan-h, hyperbolic tangent. You can set your number of layers, and you can set what optimizer. Usually use Atom, but there's other ones as well. And this one here shows you, it just gives you a kind of a scratch pad that you can play around with and try to optimize it. It shows you, and this one I did do some optimization on here. It's a 3.7 for the auto MPG. We'll run it again, 3.6. You can try various things. So if I take that and make the second hidden layer just 1, it probably won't do as good. It's taking a little longer to train. $13, yeah, not nearly as good. But you can experiment with these and see if certain things really help. Like we could add 10 to each of those. That's gigantic. See if that helps it any. It will take longer to train. Or not. It ended up stopping after just 71 iterations. So even though it took longer, or even though it's a much bigger, it did get a slightly better score. And it took fewer iterations, but it's a much more complicated neural network. So you need to kind of decide as you play around with these and create more. You can try even You can try a variety of things. You can try, this is often how I optimize these. You could make this one 100, 50, and then 25. You'll notice usually I do start out with a bigger number and sort of half my way down. If I run that, 3.55. So that's decent. That additional layer might have helped some, or that might not be a statistically significant change. But you can keep experimenting with this. The best I've ever gotten with AutoMPG is maybe about 2.9, because there is definitely some noise in that data set. All right, this is the end of the module. Thank you very much for watching. And we will continue with Module 5.